Welcome back, everybody. In this video, we are going to prove a sequential characterization of Darboux integrability. It keeps in the theming we've had done all class, right? Every sequence or every concept we had some sort of a sequential version of it, and so it only makes sense we should have one for integration. It's actually going to be very useful for us. In the next video, we're going to do an example, namely the indicator function of the Cantor set. And we're going to use the sequential characterization to show that that indicator function is integrable. All right, so let's get to it. So in our theorem, well, we have our usual setup. I have a bounded function on the closed interval AB. And so the statement is that f is integrable. Of course, we always mean Darboux integrable in this class, if and only if. Okay, so we want to exist a sequence. Okay, but what is the sequence going to be? Unlike with sequential characterization, say, of functional limits or continuity or whatever, we don't want a sequence of numbers. We actually want a sequence of partitions. Okay, this has something to do with integrals, right? So we're going to look for a PAB sequence. So remember, this PAB meant all the partitions of the interval AB. So how are we going to denote this? So what I'm going to do is I'm going to use my normal notation for a partition. And then as an upper index, I'm going to use my normal notation for a sequence. So we are going to have things like w square 1 and w square 2 and w square 3, etc. Okay. In class, I was using an alternate notation with a square and then a dot outside, but this is a little more condensed. I like it. Okay, so there's going to exist this sequence of partitions such that if I look at the difference between the upper sum I'm going to think of the upper sum like this UF now as a function. You give it a partition, it spits out a number. So I can apply it to the sequence of partitions. So I'm going to get a sequence of numbers. And then I'm going to subtract the lower sums applied to this same sequence of partitions. And what I want, well, based on the integrability criterion, we want these to get close to each other. So in the limit, as I get through these sequences of partitions, I want this to go to 0. Okay, and then I get a special case now. So in this case, so where f is integrable and there is this sequence, yada yada, if I compute the limit of just the upper sum applied to this partition, or sequence of partitions, it will give me the exact same thing as if I took the lower sum and took the limit of that. And what is it that it's giving me? Of course, it's actually giving me the value of the integral of f. All right, so that is the sequential characterization. Like I said, in the next video, we'll actually do an example where we use this. But for now, I just want to give a proof. So the proof is not going to be terribly complicated, especially for this first part. So let's first assume that f is integrable. All right, well, we know by the integrability criterion for any epsilon, I can find a partition such that the difference of the upper and lower sums is less than epsilon. I do that for any epsilon I like. So what I want to do, since I want to build a sequence of partitions, is I'm going to build a partition for each positive integer. And how is that going to translate into my epsilons? Well, I'll just take my positive integers and look at their reciprocals. Okay, so then for each positive integer n, I'm going to let w square n be a partition such that the difference of uf applied to wn and lf applied to wn is less than epsilon. Okay, and as I said, this is possible by the integrability criterion. Okay, I think it's pretty darn useful. Okay, oh wait, what's our epsilon? Hey, epsilon is 1 over n. Almost messed that up. Okay, so that's the epsilon we want is going to be 1 over n. According we do for any positive number. Okay, but if I know that I have this sequence such that for any n, I know that this difference is less than 1 over n, well, this exactly tells me that the limit of uf applied to this sequence minus lf applied to this sequence is equal to 0. I mean, that's exactly what it means for a limit of a sequence to be 0, right? You go out far enough, you can get as small as you like. Okay, so that's one direction. So conversely, so conversely, I want to show that f is integrable. So that means I can use again the integrability criterion. I need to get the upper and lower sums to be within epsilon or some constant multiple of epsilon. So let me let epsilon be greater than 0. Well, now we get to assume that we have partitions, right? And I'll just use the partitions given in the problem. Since the limit of the difference applied to these partitions is 0, that means that there exists some m, all right, and got far enough. So there exists some positive integer m such that if little m is at least big M, then, well, take a particular group, right, where you use a little m here, then the difference between UF, W square little m, and LF, W square little m, is less than epsilon. But this is precisely what the integrability criterion asks me to do. So, by the integrability criterion, f is integrable. Okay, so that actually is not so bad. So what about this other statement, right? That the limit, if you just look at either the upper sums or the lower sums, that this actually equals the integral. So I'm going to prove this first equality. The second one is done essentially the same way. He's got to change things where they need to be changed. Okay. So since I want to show that the limit of the upper sums is equal to this integral, then I'm going to look at the absolute value of the difference between the upper sum and this integral and show that I can get that absolute value to be less than epsilon for any epsilon. So I guess I need an epsilon again, right? Okay, so next part, let epsilon be greater than 0. All right, so since f is integrable, okay, that's nice, we're in that situation. I know that the integral of f is equal to the lower integral of f. It's also equal to the upper integral of f, which if you're going to do the other equality, that's probably what you want to write down. Okay. Furthermore, by what we just set up above, right, we know there's this big M. Okay, that's what we have right here. So, and there exists M, positive integer, such that if little m is at least big M, then the difference in the upper sums and the lower sums is less than epsilon. Okay, again, using, right, the same sequence of partitions, right? We get to use both of these now. Great. Okay, so just a little general comment now. We know that upper sums are always at least as big as lower sums for the same function. And that means that any upper sum will be an upper bound for the set of all lower sums for the same function. Okay, but that means if it's an upper bound, then it is at least as big as the supremum of all of the lower sums. Oh, but the supremum of all the lower sums is the lower integral. So that tells you that any upper sum is at least as big as the lower integral. Okay, so on the side, any UF is at least as big as the lower integral for F. Okay, so let's just keep that in mind. Okay, so what can we do with that? So we need to look at the difference between UF applied to, okay, well, let's look at this mth term and, well, the integral for F. We want to show we can get this less than epsilon. That will show that the limit as m goes to infinity, right? The limit of this, of the u's is going to equal the integral of F. Okay, now I can replace the integral of F with the lower integral of F. And when I do, I can drop the absolute values because I know that the upper sums are at least as big as the integral. So I drop the absolute value and I replace the integral with the lower integral. Okay, now I know, let me just copy the upper integral. Oops. I know what the lower integral equals. This is just the supremum of all lower sums. So now I'm going to work over all partitions. So let's call them X, say. Okay, but if I replace the supremum of all the lower sums with just one specific lower sum, then that lower sum should be less than or equal to this supremum. And because it's less than or equal to it, that means we're going to be getting a bigger difference. So this is going to be less than what I would get, or less than or equal to, what I would get if I looked at the upper sum minus any particular lower sum. And so how about as a particular lower sum, I use the exact same partition, Wm. Because I know that that difference is less than epsilon. Hey, we just did it. We got that the upper sum and the integral are within epsilon of each other for any epsilon. Okay, so this is going to complete the proof. Fantastic. Okay, so like I said, we're going to be using the sequential characterization as a way of proving integrability for the indicator function of the Cantor set, and that'll come in the next video. We'll see you there.